So with this section, we're going to start our discussion on derivatives. Now, before, we had this idea of rate of change, right? If we have the slope, we know that's something like y2 minus y1 over x2 minus x1, right? And this is if we have a line where we write y equals mx plus b. This value for m is this slope value right there, right? Or another form, so again, this is a slope intercept form because we have slope and then we have the intercept, right? The y-intercept. And then we have point slope form, y minus y1 equals m times x minus x1. And this is point slope form of a line where x1, y1 is just some coordinate on that line that we wish to consider. Well, let's emphasize right here, slope is something we talk about in the context of lines. Well, we started saying, well, let's say that I have some function whose graph maybe looks something like this. And maybe I want to talk about the rate of change from this point to this point. And I say the average rate of change is given by this idea of the slope, right? If I make a line that goes between these 2 points, then I can make a secant line. And that's in yellow, which is probably the worst color to use on a white background, so I'm not going to repeat that. But I think we can kind of see the drawing here. This yellow line is what we call the secant line, and that connects 2 points together. So we can talk about the rate of change from a value like if I call this x1 over to x2. Okay, well, what if, right, think of yourself driving. So maybe in this example, the x value is time, and maybe this graph here for the y value is distance. So you tell me the time, and I tell you how far you've driven. We plug in t, or a time, into this function, and it gives me how far we've gone. Now, if we were to talk about the rate of change, if you've driven 10 miles, and it's taken you an hour to do that, then we would say you drove at a rate of 10 miles per hour, right? So a really normal conversation to have about rates of change is speed, right? Our speed is the rate of change of distance per time, right? We say 70 miles per hour, something like that. But we don't only talk about speed as something that happens over an interval of time, right? When you are driving, you see that the speedometer, I forgot the word for it, says how fast you're going, right? We see these signs that say 70 miles per hour, and it's telling you how fast you're going at that moment. It doesn't mean that you've driven long enough for it to tell you how far you've gone, right? Just by moving the vehicle, it tells you the speed that you're going. So speed, a rate of change, should happen at an instant. We should have some idea of an instantaneous rate of change. Well, the way that we do this is actually built from our concept of slope, the same idea of slope that we're used to. Now, oh, excuse me, if I want to know my slope, sorry, my rate of change at a point, then maybe I want to take x values that are closer and closer together. So considering this for my slope, if I want to know the instantaneous rate of change, maybe on bottom at the x value, let's say 1, and then I plug 1 into my function to get that y value, right? Maybe we look something like this if I'm just wanting to consider the rate of change near 1 and some other point. Well, I need to let this value for x get really, really, really close to 1. Well, why can't I just plug 1 in? Well, if I have f of 1 minus f of 1 over 1 minus 1, that would just give me 0 over 0, which is, well, for 1, we can't divide by 0, and even more so, 0 over 0 looks even worse, right? In terms of limits, we would call that indeterminate form. But we're not taking limits, so this just straight up, in this case, does not exist, right? There were no limits to be had here, so this doesn't exist. However, what if we do try to take a limit? If I can't literally do 0 over 0, if I can't plug the same value in for both of my x's here, then what if I just say one x gets infinitely close to the other? So our instantaneous rate of change, aka the derivative of a function f of x at a number a, we also write as f prime of a, and that notation will make a lot more sense later on. F prime of a, the derivative of f at a, instantaneous rate of change of f at a, is the limit as x goes to a of, we're going to do a minus x on bottom for our x values, and then on top, f of a minus f of x. So this same idea of slope, but because I can't genuinely plug in the same number twice, I have to take a limit and try and talk about getting infinitely close to that value on both parts. Which, if we just try to plug it in, would give us indeterminate form, right? 0 over 0. But remember our conversation about limits is that when we have 0 over 0, that doesn't mean we're done and it doesn't exist. That means there's more work to be done. We call it indeterminate form because I cannot determine what the limit is in that form. However, the limit written differently might exist. So, that is the definition of the limit. So let's clean the page up here. And let's do another, there we go. I still haven't figured out how to make the eraser bigger. maybe I'll cut this from the video. Maybe I'll leave it in to give us time to write things down and catch up and just think about what we're doing. So just from this definition that we have right here, if we're looking at the function x squared, if this is f of x, then f prime of x, and let's say at 1 would be the limit as x goes to 1, right? I'm just copying the definition from down here. Limit as x goes to 1, f of 1 minus f of x over 1 minus x. Well, I know what the function f is, so I can plug in f of 1 is 1 squared, f of x is x squared. So we look like 1. Oh, forgot to write limit out front. So we have the limit as x goes to 1 of 1 minus x squared over 1 minus x. Now we notice these look a lot alike, and it turns out 1 minus x squared can be factored as 1 minus x times 1 plus x. This is a difference of squares because x squared is x times x, and 1 is 1 times 1. So if we multiply these terms all the way up here, the middle part should cancel and we'd be left with nothing but 1 minus x squared. So I can rewrite this as the limit as x goes to 1 of 1 minus x times 1 plus x all over 1 minus x. And with our limits, we can cancel our terms just like that. So this is the limit as x goes to 1 of, I'm left with 1 plus x over 1. Well, this is now nice and clean and continuous, so I get to just plug in my limit for this function. So this is 1 plus 1 over 1, which is just 2 over 1, which happens to just be 2. Okay, so from the definition of this limit, I found out that the rate of change of the function at 1 is 2. Well, what does that mean graphically? Well, if we graph our function x squared, to the left we go like that, to the right we go like that, and if this is 1, this is 1, then I'll make it in red. At this value, our slope, if we zoomed in really, 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 really close, that's as close as MS Paint will let me get, I guess, this almost can look like a flat line. So if I draw that flat line going out forever and ever and ever, right, this looks like a y equals mx plus b. And that value for m, we figured out the slope is 2. Well, can I figure out what the rest of the function is? Well, yeah, I know I intersect this point, 1 comma 1. So, in point slope form, I have y minus 1 is equal to 2 times x minus 1. And I can solve this for y. I have 2x, and then I distribute the 2 to the negative 1 minus 2. And then I add 1 to both sides to move that negative 1 over. Oh. So I have y equals 2x minus 2 plus 1. So really I have 2x minus 1. So the slope at 1, sorry I had to cough, I muted the microphone. The slope at this coordinate looks like 2, and the line that it looks like when I zoom in really, really, really tight looks like the line y equals 2x minus 1. Now, this idea of this line at that value is what we call the tangent line. So let's think about this in context of Earth. So let me zoom out a reasonable amount. I have to cough again. Sorry. So let's zoom out a reasonable amount. This looks nice. And I'll scroll down and I'll draw a picture of our wonderful planet. So I think it's okay to say that the Earth is round, right? However, if you are right here, if you look around you, you will notice that the Earth doesn't look round, right? Because if we zoom in to the normal human's perspective, right, it looks something like this, right? There you are, walking on the Earth. You don't feel like you're about to fall off of it, right? It doesn't feel like it has some crazy curve going on. But if you zoom out and look at the Earth from space, you can see that it absolutely is round. But because we zoomed in so tightly, it looks flat. We're such a small piece on this huge planet that it feels flat to us at a given spot. Well, that's not really fair to say, actually, because maybe in a slightly different spot over here, maybe you walk, this is a huge distance, truly speaking, but if I zoom in on maybe this part over here, the Earth isn't always flat. Sometimes people climb up mountains. That's possibly the worst mountain ever drawn. Let me redo that a little bit. Sometimes people climb up mountains. And if you have a toboggan on, you look like that, okay? Right? And your hiking gear, you look like that. So, we zoomed in a lot, and now you're walking up this way. And there is some elevation, right? The mountain is going up. Over here, on this flat ground, it would look flat. Over here on the mountain, it looks like you're going up. Maybe somewhere else, you're walking and it's going downhill, right? Now your elevation is going downwards. So even though this big, huge Earth is round, if we zoom in on really specific spots, like how the tiny human beings we are, we experience that local elevation, there is still a slope at the individual point on the planet Earth, even though it looks round and like a curve that we wouldn't be able to tell the slope of, right? So that is the exact same thing happening with our functions. Even though this parabola doesn't look like a line, if we zoom in really, really, really close, oh, I'm pressing the wrong button. Where are we? If we zoom in really, really, really close, it would turn out that I can kind of make out a line at an individual value, right? If I'm looking right here, then it looks like I'm about that line. Also, I'll do this in green. If I'm on the very bottom here, it looks like we flatten out, right? If I'm on the bottom of that parabola, it kind of feels like I would be on flat land. So, as you walk along the function, it's kind of like how we are people on Earth. Even though the Earth is round, when we zoom in really tightly and experience things as this tiny little dot on this huge planet, we can see the slope, the local elevation, the derivative, and the instantaneous rate of change. So that is the derivative at a value, the instantaneous rate of change, the local elevation, and the slope of the tangent line. Those lines that we draw that touch the graph at that point, where we zoom in really, really, really close and we look like the graph at that point, those are our tangent lines. So this is slope of tangent line at that value that we called A, right? Slope of the tangent line at A is the derivative of f of x at A. Very good. Now, the uh, derivative, actually, the thing that I was about to say is something we talk about in 2.2 in the next section. So this is the idea behind the derivative. It is the local elevation, the instantaneous rate of change, the derivative of f of x at A. And one more thing. The units of a rate of change is outputs per input, right? If its distance is miles and time is hours, we say miles per hour. If it's, think of a factory and they make bicycles and they make so many bicycles in a given day, then you might say the rate of change of the production of bicycles would be in bicycles per day. Outputs per input. Always filling in the blank like that. Okay, so that's the basic idea of where our derivative is and what it comes from. Oh, and it turns out there is a slightly different way that we can tweak this definition of the derivative that makes things a little bit easier. So let me erase all of our planet journeying. I've never been on a mountain. Oklahoma is actually home to what is called the world's largest hill. Now, how in the world can Oklahoma have the world's largest anything? Well, pretty close to my hometown, there is a statue of the world's largest peanut. Turns out that isn't true, hasn't been true in a very long time, but Durant still has a statue of the world's largest peanut. And Poto, Oklahoma, Potau, I think is how you spell it, is actually home to the world's largest hill. How is it the world's largest hill? Because, let me draw it. This is the hill, and this, as the men minimum height of mountains. It is 1 foot away from being a mountain, or maybe an inch or something like that, maybe like 2 inches. Essentially, if the hill was any taller, it would be a mountain. So they claim they're the world's largest hill because anything that would be bigger would be classified as a mountain, not a hill. So that's fun. I don't have any idea why I started talking about that. Anyway, so what if we tweak? Oh, I never been on a mountain. I also haven't been on the world's largest hill, regardless. So it turns out we can tweak this definition of the derivative ever so slightly. So the idea here is that the difference between a and x goes to 0, right? Because I'm saying my points, this limit, right, are getting closer and closer and closer to a. We're getting infinitely close to this value a. So what if, instead of changing my value x, what if instead I was looking at their difference going to 0? So if I'm taking the limit at a value a, then how can I represent something that is going to be just a little bit bigger than a? Well, I can introduce a variable h and let h go to 0. So if this is the first point, and then a is the second point, then the difference between a and h is going to 0, right? A plus h as h goes to 0 is getting infinitely close to a. So we rewrite this to be f of a plus h minus f of a over a plus h minus a. Well, on bottom, a plus h minus a disappears and just turns to h. So now we have f of a plus h minus f of a. And it turns out that when we set things up like this, it's actually going to radically simplify or rewrite what taking its derivative actually is. So it turns out that this setup that looks exactly like rise over run actually turns into this setup. They end up being equivalent. If one of them works, the other one works. But again, this is the limit as h goes to 0. The limit as h goes to 0. So this is a perfectly equivalent definition of the derivative. Just rewritten. So not only is f prime of a, as we call it, the derivative of f at a, equal to the limit as x goes to a of f of a minus f of x over a minus x, we also get to write it as the limit as h goes to 0 of f of a plus h minus f of a all over h. So, does that work out nicely? Let's look at what we did earlier when we found the derivative of x squared at 1. Well, now f prime of 1, using the h definition, the limit as h goes to 0 of f of 1 plus h minus f of 1 over h. Well, our function was f of x is x squared. So we're plugging 1 plus h into x squared, and then subtracting what we get when we plug in 1 into x squared. Well, 1 times 1 is 1, so that's just going to be 1. This is over h. And I forgot to write the limit out front. Let me squeeze it in there. Limit as h goes to 0. Well, now I can expand out 1 plus h squared, right? This is 1 plus h times 1 plus h. 1 times 1 is 1. 1 times h is h times 1 is h, and h times h is h squared. So this is 1 plus 2h plus h squared. So I write 1 plus 2h plus h squared minus 1 all over h, and I keep forgetting to write the limit first. The limit as h goes to 0. Now we can simplify. I have a plus 1 on top and then a minus 1 at the end here. So those are going to cancel and give me 2h plus h squared, and all of this is over h. Now if I just plugged in 0, this would look like 2 times 0 plus 0 squared over 0, which is going to give us 0 over 0. So we don't want to do that quite yet, and whenever we have this h on bottom, it should always turn out to cancel with something on top. Maybe we have to do some algebraic manipulation. But in this case, oh, it's already kind of set up to cancel with an h on both terms there, right? Limit as h goes to 0. I have an h with the 2. 2h divided by h is just 2. H squared divided by h is h. Now the limit as h goes to 0 of 2 plus h, I get to just plug this in now. So this is 2 plus 0. Well, that's just 2. So it turns out the derivative at 1 is 2, which is exactly what we got before. But instead of having to divide these terms out, I really only expanded 1 plus h squared into this other term. Now, with a more complicated function, both of these derivatives are going to look a bit messier, but we can still use either of these formulations, or either of these formulas for our limit. Now, it turns out which one you choose is entirely up to you. It is a matter of preference. Now, this one, the top one, generally speaking, is a little bit more algebraically involved, right? You had to do this division right here. Now, this turned out to be an instance where the division was really nice and clean, but it is not always going to be the case that these functions factor out in really nice ways. So, it is probably going to cancel, but getting there, doing that division, isn't always nice and clean. On the other hand, all you had to do with our limit as h goes to 0 definition of the limit was expand it out in a nice way. You just simplified what you had in front of you. So in that sense, it maybe is a little bit easier, but more algebraically, like you had to do some more calculations maybe. Whereas on top, you just had to be clever with how you use the algebra to rewrite it. So the work is kind of up to you to decide what you prefer to do. Anyways, that's 2.1. We have two formulas for the derivative, and they both give us the slope of the tangent line at A, the rate of change at that point, instantaneous rate of change. Very good. I still don't know what to say to end this. Bye bye.